Hi, I'm Spencer Banta, and welcome to the Wavetronics webinar. We're excited to have you here today to talk a little bit about dilemma zone protection and how continuous tracking advanced detection can make your intersections more safe. Here with me today, I have some help from Dan Dukowitz and Chase Clark. They'll be our moderators for this. We invite you to ask some questions as we go along. This Skype for Broadcast service that we're using will put a slight delay in the video broadcast. But if you ask questions while we go through the presentation, we can make sure to answer all those questions at the end. So thank you again for coming, and we're just gonna jump in right now. We're gonna get started. So the first thing that we're going to talk about is take a look at this video. So the year was 2006 when we first came out with the SmartSensor Advance. We were doing some testing on it, and while we were recording some of the video with it, we saw that there was a unique situation that happened. And as you can see here, a truck is going around a car to prevent a rear-end collision. So we looked at this video and we thought, what's happening here? Why is this? What's going on? There are two different vehicles with two different dilemma zones. We identified this problem. We went to work to fix it. Today we're going to talk about how to make your dilemma zones less of an issue so that you can have more safe phase terminations. So the dilemma zone, what we're talking about today, isn't a physical dilemma zone or what they call a type 1 dilemma zone. It is the type 2 dilemma zone, or the region 2.5 to 5.5 seconds away from the stop bar as you're approaching a green light. It's that, oh crap, do I gas or brake moment. That's the moment that we're trying to prevent. And so dilemma zone protection is the tool to do that, as you're aware. So let's first talk about dilemma zone protection and what it's defined as. It's defined as 2.5 to 5.5 seconds away from the stop bar. So in time. So let's take an example of what is commonplace in dilemma zone protection today. So if we have a vehicle at 700 feet that's traveling 50 miles per hour, let's calculate its dilemma zone. So the way we do that is we take 50 miles per hour, we convert that 50 miles per hour. I had to get that bouncing thing somewhere in my presentation. We convert that 50 miles per hour to feet per second, and we get 73.3 feet per second. We take 73.3 feet per second, times it by 5.5, take 73.3 seconds, times it by 2.5, and that gives us the inner and outer boundary of the dilemma zone for this vehicle. So that's at 403 feet and 183 feet. And you can see there in the yellow that that's the dilemma zone region. So that dilemma zone region is going to be for that vehicle. The design speed at this approach is actually 40 miles per hour. So 40 miles per hour is a little bit different than 50 miles per hour, right? So let's talk about what that is. So if we do the design speed and we do 40 miles per hour, and then we convert that to feet per second, we would get 58.6 feet per second. So 58.6 feet per second multiplied by 5.5 and then multiplied by 2.5 gives us the 322 feet and then 146 feet. So if we were to design this intersection, most likely we would put our loops right there at the 322 feet. And so the vehicles, so when the vehicles came into the approach, they would extend for 3 seconds at that 322 feet. So let's take an example here. This vehicle comes in, all right, freeze frame there. The signal goes to yellow. What had happened? Well, the vehicle hadn't quite reached its dilemma zone yet, and so it extended, so it hasn't quite extended for it. So this could be a potentially unsafe situation. Now let's talk a little bit about, let's take a look at another example on the efficiency side. So on the efficiency side, if we have vehicles coming in, freeze frame here, what happened? Well, the car is through its dilemma zone, traveling 50 miles per hour. The next car is about to enter its dilemma zone, but the intersection didn't gap out, providing it's at the end of the cycle time. It didn't gap out because it had hit the loop, it extended 3 seconds, but there's a 90% probability that this car is probably going to run the green light or run through the yellow light. And so that can create an inefficient situation. All right, now that gets compounded even more because there's two vehicles coming into the approaches at the same time, making for a less likely chance that we'd find a good gap out. So that's kind of the current situation. I want to show a couple more animations to kind of help illustrate that point that I just talked about in a moving situation. So let's watch this animation. You'll see the top vehicle is going 60 miles per hour. The bottom vehicle is going 40 miles per hour, and the design speed is 50 miles per hour. So as these cars approach the intersection, notice that the car that's going faster than the designated speed isn't being protected for a portion of it, is protected for a portion that needs to, but then overextends until it gets all the way through. The vehicle on bottom going a little bit slower, it got protection when it didn't need it, got the right protection for a portion of it, and then wasn't getting the protection it needed and ended up running through on red. So this static point detection system can cause issues for dilemma zones and dilemma zone protection. So Wavetronics kind of went to work on this to figure out what was going on, and we came up with a pretty good solution. And it has to do with what we call the SmartSensor Advance, which does continuous tracking advanced detection. So basically, it'll detect the vehicle at some distance away from the stop bar, and it will track it continuously to the stop bar. So in 2006, Wavetronics first came out with the SmartSensor Advance, and it went up to 600 feet. It provided dilemma zone protection for design speeds from 40 to 50 miles per hour and protected vehicles as it came into the intersection. We were then later, we watched that video that we watched at the beginning and realized that for truck protection, we needed to get a little bit more distance because a truck's dilemma zone is a little bit larger, from 7.5 to 2.5 seconds instead of 5.5 to 2.5 seconds. And so we went to work figuring out how could we make that work. And we created another device, the SmartSensor Advance Extended Range, that can detect up to 900 feet away from the stop bar. And typically you'll see vehicles come in for the extended range about 800 feet. You'll see the large trucks come in about 800 feet, and then the cars will come in about 500 feet for the normal advanced sensor. So let me show you how it's a little bit different than a static point detector because we're continuously tracking. Notice the blue shape here is the entire footprint of the SmartSensor Advance. The blue square that we're looking at there is the typical dilemma zone for the vehicle that's traveling 50 miles per hour. Now in this case, the vehicle is going to be changing speeds, for whatever reason. They're coming to an intersection, and that's a very flux place for vehicle speeds. So let's watch this animation and see how it works. So that vehicle is traveling 50, slows down, and the dilemma zone changes with the vehicle. And so if the vehicle is going faster than the designated speed, the dilemma zone moves with the vehicle. If the dilemma zone is moving slower than the speed, then again, it moves with the vehicle. You'll notice that the end result is that both vehicles make it through on yellow, which is the intended result. So here's a side-by-side comparison of the two. Notice that on the top we have the loop detection, and the places where these normal traveling speeds, it's not ridiculous for a car to be going 10 miles faster or slower any approach, are actually being protected, or where there's a safety or efficiency concern. But in order for this to happen, there need to be some other changes. Some of those changes need to occur in the controller. The controller needs to have the passage time changed. I've seen some of you traffic engineers move your hands that fast. I'm not quite there yet, but I'll get there. So that passage time, so you go to the controller, and you normally would have a 3, 5, 6 second extension for that car to get safely to the intersection. But you can lower the passage time now, because the way that it works is the Advance continuously puts a call into the controller saying, hey, there's a car here, protect it. Hey, there's a car here, protect it. And that passage time keeps that vehicle safe until it's passed through that point. I'll show an animation here in a minute. So again, just to reiterate my point. So with the traditional loop system, if you have a 3-second passage time, you're always trying to get to that 0. But when a vehicle hits a loop, it extends 3 seconds, it extends 3 seconds, it extends 3 seconds. With the SmartSensor Advance, instead of continually extending 3 seconds, you can hold it at 1 second or a half second, depending on your roadway. And you hold it, hold it, hold it until the car's no longer in the dilemma zone, and then you drop it down. And you'll notice that once that back car is out of the dilemma zone, it'll just, that call will go out of the controller, and it'll attempt to gap out. And in this case, it will gap out. So to review, so this is an exciting piece of information here, right? That we've created a radar device that continuously tracks the vehicle. So the big takeaway here is that the SmartSensor Advance protects vehicles traveling at speeds other than the speed limit. If every vehicle is traveling the speed limit, then a static point detection system would work. But in this case, where vehicles are always changing speeds at the intersection, the radar device, the Wavetronic SmartSensor Advance, can help track the vehicles as they come into the intersection. So we're going to change gears a little bit here, and I'm actually going to show you a setup and some of the configuration in the software. Before I jump to that, though, I do want to give some of the results that we've seen from the SmartSensor Advance. It's not a new product. It's been out for almost 11 years now, and there's been a lot of testing, and there's a lot of agencies that have fully adopted the SmartSensor Advance. So let me just give two examples here. So one was a Bradley University study where they found that there was a 58% reduction in red light running with the SmartSensor Advance compared to loops. Quite a sizable and significant reduction of red light running. Ohio did another study, and in that study they were just measuring intersection accidents over time. And what they found is that intersections, what they put the SmartSensor Advance in, more rural intersections in this case, that they had a 38 to 100% reduction. Engineers could go back and forth all day on 100% reduction, right? But I think there were accidents before, and then there were no accidents, right? But 100% reduction, yeah, anyway, we don't need to geek out about that. But the moral of the story is the continuous tracking helps the Advance helps the intersections to safely terminate their phases. All right, so now moving on to that example that I was talking about. So let me explain a little bit about the UI, because we're going to watch a video here in a minute that kind of shows all of those things working together. So if I were to set up a dilemma zone protection for cars, notice that that's the L2 light indicator here. So this call represents a call that would just be made into the controller, a typical extend call. This green bar here signifies that L2 is making a call into that controller. Notice at the bottom we have range, speed, and ETA. That on the left side here, the range of that vehicle at this particular moment in time is 275 feet. The speed of that vehicle is 42 miles per hour, and the estimated time of arrival is 4.4, which is in the middle of the 2.5 to 5.5 seconds. And so these are the settings that are controlling this indicator here. So notice there's a range indicator here. The range here is from 100 to 720 feet. So basically anywhere in the approach. The speed has to be going over 35 miles per hour. This is probably a 40 mile per hour approach that this intersection was on. And so that's why the speed is set at 35 miles per hour. And then the ETA is 2.5 to 5.5 seconds. You'll notice that the car underneath it, even though it has an ETA of 3.5, it doesn't meet the speed criteria. And so this vehicle is not going to be put a call into the controller, because at this point, the engineer has decided that a car will safely terminate. The phase will safely terminate with not giving a call to that particular vehicle. And so this is a typical setup for a dilemma zone protection for cars. Let me show you one for a truck now that could be on the same call. This is what we call the L1 indicator here. So that L1 is level 1, or a priority call, if you would, or a large profile call would probably be a better way to put that, where the settings are all similar on the range and the speed, except for the ETA. The ETA is 2.5 to 7.5 seconds. So as this truck continues to come to the approach, the vehicle that's at the very top point, near the CH1-A1 in the top part of the screen, the range is 765 feet away from the stop bar. The speed is going at 31, and the ETA is 16.8 seconds. So not until that ETA is 7.5 and the speed is over 35 miles an hour will a call be placed in the controller. So the engineer can kind of decide. He knows the roadway the best. He or she can kind of decide what is the best settings for the controller and for the sensor. And then we, of course, provide feedback for that as well. And lastly, one of the last applications that we do is called queue reduction. Notice that this vehicle here, so this is going to be most used on your intersections that don't have stop bar detection, that are frequently on min recall, and that are your main corridor or your main line roadways. And notice the settings here. So we put we have two filters active. One of the filters is from 100 to 155 feet, and the speed is going from 1 to 35 miles per hour. And so what this can be used for is to extend the call early on in the phase. So you can extend and say, okay, hey, we need to keep this light green to get this queue out of here. And I'll show you the video here in a minute. But notice that that's the call going there on the queue portion of it there. And this vehicle got a call because it's going slower than 35 miles per hour and is within the 100 to 135 feet from the stop bar. All right, so this is my favorite part. So this animation kind of shows all of the things happening at once. So you'll notice here we have the Q, we have the L2 and the L1 again. And then over here we have a little clock that kind of represents the cycle time for this controller. And so I'm going to play it here and then we'll talk about it. So notice on startup, the vehicles that we just got our green, it's in the min green now. We've lowered our min green substantially. And now the sensor is going to output at the controller saying, hey, there's cars still here in a queue. We need to keep it green. We need to keep it green until the next vehicles come to the approach. Now, as the vehicles are starting to flow in from the next platoon arriving, that L2 light is indicated, signifying that there are plenty of vehicles here that are meeting the criteria of going faster than 35 miles an hour and then between 2.5 and 5.5 seconds. You'll notice that semi-truck is starting to come into the picture there. And that truck is outputting to the controller a little bit longer than for the cars because of its size. And it outputted until all of the cars are safely through and they found a significant gap, and then we'll achieve gap out right there and we'll gap the intersection out, providing the other side, of course, has a gap as well. Finding a safe phase termination. This was obviously an exaggerated example, but it can, because the vehicles aren't all traveling 40 miles an hour exactly, the SmartSensor Advance does a good job at finding those gaps and safely terminating the intersections phase. So Randy Ensel, project manager in Florida, was going to put loops on a project similar to this, where he was going to be doing multiple of these things. But what he found is that it became somewhat cost prohibitive to do all that trenching and work to get all those loops in the different places that he needed. And he found with the SmartSensor Advance that he could do multiple things or multiple applications with just one sensor. And so he used the SmartSensor Advance on some of his projects. I'm going to change gears a little bit here now, and I'm going to talk a little bit about cabinet integration. So we have multiple ways for these calls to get into the controller. The most common and the simple way that everyone's familiar with is through rack cards. Most detection devices use rack cards, and ours was no different. So we have a little surge protection and communication device here in the middle yellow square, and then that would put calls up into the rack cards, and those rack cards would make the call to the controller. The controller had a lower passage time, and that would be how the call would go all the way to the controller. Now, we've recently come out with a new device. The Click 650 and the Click 656 are cabinet integration devices that have SDLC on them. So for your NEMA Type 2 cabinets, you'll be able to get your calls straight into your BIU, BIUs 9, 10, 11, and 12, without having to do rack cards. So that means that you can get multiple channels, and you basically do what you can do with software instead of using the hardware. And then there are some integrations into 2070 cabinets as well. But there are some things that you need in your controller, your 2070 controllers, like a 2E I/O card. Those things can, if you have that card, you can do an SIU to BIU, a serial interface to a BIU connection to get the calls into the controller that way. And the software has to be made for it as well. But that can significantly minimize the amount of cabinet space you have to use by using the Click 656. And again, the Click 656 can handle up to 6 sensors, and the Click 650 can handle up to 4 sensors.
And so that's what this little animation shows, is that you can go from either click 650 or click 656, and then go straight into the controller. And so that can minimize your cost significantly. All right, so now I'm going to jump into a little bit about the design. So mounting location is important for any detection device that's non-intrusive to help minimize occlusion and help maximize detections. And so some of those detection positions for the SmartSensor Advance are here. So A is the most ideal detection spot for the equipment for the SmartSensor Advance. B is also a potential option there that you'll see on the side. C on the other side. The sensor needs to be mounted at least 17 feet in the air. And then D. And D you would use if you wanted to measure red light running or something to that effect. Or maybe more optimal hue detection. The important thing is that it needs to be within 50 feet. The sensor needs to be within 50 feet of the middle of the detection area. So there are a lot of mast arms out there that just have a cement pole, for example, in the place of C or B. And so in that case, we would frequently recommend just to put it at C and put it about 30 feet in the air. Anywhere above 17 and under 50 would work, but in the middle region there is about the best. And then just pointing at the detection area. So one of the most significant things about the Advance is that that it's non-intrusive, and that gets people out of the road. Dave Townsend was on the UDOT signals team, and his job was to go out and locate loops in the middle of the roadway. So as you can imagine, that wouldn't be too fun of a job to have cars whirring by. Well, it's something we've all done. But when cars are whirring by you, it can be a little bit, it can cause some anxiety. And so he recommended to the signals team, hey, why don't we change the policy? And so the policy was changed to only use SmartSensor Advance, keep people out of the roadway, and to continuously track the vehicles in for safety. So for 2 safety reasons, they changed the policy to only use SmartSensor Advance on 40+ mile/hour roadways. One of the things that we do in our design as well to help people when they're designing our projects newly is we do have a team of engineers here who can help review your plans. So you can contact them at support@wavetronics.com. But you can send them the plans and they'll help provide you. We can also provide you CAD drawings. And this is just a CAD drawing of the sensor's mounting. You'll see here that there's the sensor head, the mounting bracket. You can see a grounding lug, grounding wire there, and then the actual communication wire and how it can go into a pole. It's fairly simple, the mounting of these products is. And so providing the right things on the plans can make sure that contractors install them accurately. And that's something that Wavetronics is happy to help with, and very good at it as well. One of the designations that you can use for the sensor is a CTAD detector on your plans. So calling it a CTAD detector, the continuous tracking advanced detection, helps contractors differentiate the mounting locations from the RPD, or radar presence detector, or RVPD, radar vehicle presence detector, that is used for stop bar detection. And so the mounting location, as you can see on these plans, we also have these footprints that we can provide. So the 3 most important things to put on your plans is mounting location, specify that it needs to be a continuous tracking advanced detector, and then lastly, lowering the passage time. The passage time does need to be lowered. There'll have to be some communication there because it is different than a static point detector, like a loop or a puck or a video. But those are the 3 things that need to be specified in the plans. And again, Wavetronics is happy to help. We got a good team here that's done that. So I just wanted to touch before we wrap up here, I just wanted to explain one of the really cool things about the SmartSensor Advance. If you use the SmartSensor Advance to detect the vehicles in advance of the intersection, and they're continuously tracking in, you can make your intersections really snappy because you're going to be getting vehicles through on the main line, and then coupled with the SmartSensor matrix on the minor movements with long detection zones, you can lower the passage time both for your advanced detection, and with a long detection zone, you can do it for your minor movements as well, gapping out as soon as vehicles are no longer present. That's a really exciting application, but we'll have a webinar more about that another time. So that's all for that one. So thank you very much. We're going to go now. We're going to see if we have any questions to go through. So I have Dan Duquitz, Stephen Bills, and Chase Clark here with me to help me see if there's any questions. Looks like we do have one question. Let me fast forward here. It's about I do have a slide on it. Perfect. It's about how does the SmartSensor Advance work in coordination. So in coordination, there's a setting in your controller called coordinated actuated signal timing. And what coordinated and actuated signal timing does is basically it borrows a little bit of time from the end of your coordinated corridors to find a safe point to try and terminate the phase. And so think of it as flex time at the end of your coordinations, where there's what they call a yield point. At that point, it's going to just look for gapping out and then servicing the other side street a little bit early. So your minor movement may come to green a little bit early, but it can also help, so it can help make sure that there's a safe phase termination there. We do have some application engineers that can help answer any questions that you have with that. And I'll answer any questions as well. My email was on that slide, spencer.banta@wavetronics.com. I'd be happy to answer any questions that you had regarding this webinar today. We thank you very much for your time. Please, again, feel free to share this with any coworkers that you have. And stay classy, traffic engineers.